Today, what I wanted to share is the use of some DynoChem models in order to investigate or interrogate gas-liquid systems. I particularly want to highlight how gas-liquid systems can be modeled using, kind of a consistent framework across a wide variety of unit operations. I think, typical operations such as distillation, kind of come to mind when you think vapor-liquid equilibria. But what we want to look at is, some unique operations, focused around, the interchange or the interplay between the contents of a vapor and liquid phase and how various process parameters and how, vessel characterization or characteristics are going to impact the performance of a particular process. I'm going to kind of approach this through a kind of a series of case studies, so 3 case studies in particular. And again, each of those case studies are going to start with a very similar kind of model framework. And then hopefully you'll see that by making very minor modifications to that model framework, we can actually address modeling questions across a variety of unit operations. So the first case study that I'm going to talk about is solvent dehydration or solvent drying or potentially even solvent degassing using a series of vacuum and pressure purges. I'm also going to talk about removing sulfur dioxide from what we call an associative solvent system. We'll talk a little bit more about that. As well as doing some vessel characterization work and some process optimization work for a biocatalytic oxidation reaction. Each of these 3 case studies kind of shares, some commonality in the fact that what we're really interested in is how gas, either dissolved gases or low-level solvents are exchanged between vapor, liquid, and how that's kind of handled throughout the system. So I'm going to kind of jump right in. The first study, like I said, solvent drying using vacuum and pressure purges. In this particularly, we had an interest in this for a recent project we were supporting where the reaction itself actually had very exquisite sensitivity to water content, right? And the commercially available solvent that was delivered for this particular reagent or for this reaction was potentially not at a sufficiently low level of water content in order to enable the reaction to execute at its highest level. The other thing is, this model would also be good for systems where dissolved gases may be present as well. So if you want to do a deoxygenation of a solvent prior to use, if you have a reaction that is very sensitive to oxygen, a model like this could be beneficial. Obviously, distillation is probably one of the first tools that comes to mind, but distillation is often both energy and also, let's say, capital infrastructure intensive. You need more than just a stirred tank reactor in order to do a distillation. So what we wanted to do was investigate whether or not pressure purges, which we would typically do at the start of a batch to inert a vessel anyways, whether or not those could be augmented or modified in such a way that it would permit drying of a particular solvent. In this case, it was toluene. The other section is kind of down here where you're providing information around the components that are present in your system. Again, this is a toluene water system. And again, this has drop-down selectable. So we have an extensive solvent database. So again, a user doesn't have to go around and track down relevant parameters. But again, in this particular model, you can kind of include batch weight, the actual composition of water and toluene in the system. All of the other information that's kind of down in the vessel information and the batch information sections, that is actually information that's pulled from the database and then kind of input into the relevant tabs in a DynoChem model. So this actually pretty closely replicates the phenomena that we would expect to see in terms of rate of pressurization and depressurization as well. So this again is a simulated pressure profile. What I'm going to do here is just kind of overlay the water content for this particular system. In this system, this simulation, we were starting at 100 ppm water. And you can see that during the pressurization event, or when you're actually at high pressure, you have a relatively constant water content. But as you evacuate the headspace of that vessel, or as you depressurize, here you're going from, again, 3 bar down to about 1 bar, or roughly. You're removing 2/3 of the headspace, essentially. So what that's effectively doing is that is allowing you to, kind of remove any of the water that may be in equilibrium with the headspace, remove that, and then the next pressurization cycle that you do, you kind of repopulate that headspace with water in equilibrium with the liquids. So here's kind of schematically what the equipment would look like. You have a nitrogen sweep. This is drawn as a sweep. We generally make a distinction. A sweep is above surface addition of nitrogen. A sparge would be a subsurface addition of nitrogen. But in a system like this, you'd have a sweep here. You'd have the effluent, which would be pulled off under vacuum in this case, nitrogen, SO2, some solvent that may have evaporated. You have obviously SO2 and NMP in the system. And then you obviously have the mass transfer between the gas and the liquid phases. So this mass transfer is going to be dictated by a number of different things. So one of the things is going to be the mass transfer coefficient, right? So that's going to dictate the kinetics of evaporation, if you will. And then you also have Henry's constant. So SO2 actually turns out to be pretty well characterized by Henry's law within NMP. So one of the things that we ultimately determined that we were seeing was that while there was a significant quantity of SO2 in solution, the rate is not being reflected by that SO2 in solution because it wasn't all volatile. It was predominantly held up in a associative state or a complex with NMP that was preventing volatilization. It turns out there's some literature precedent for this. In fact, NMP is commonly used at industrial scale as a stripper for gaseous SO2. So it turns out to be really good at holding on to SO2. So there's a reaction equilibrium thermodynamic model that was identified within the literature, and it's kind of dictated by really these kind of two expressions here. So one of them here is the equilibrium between gaseous and liquid SO2, dissolved SO2. Again, this is essentially Henry's law. This is a formula can be formalized as Henry's law. And then you have a chemical reaction. Again, you have SO2 gas interacting with dissolved SO2 gas kind of interacting with NMP, forming this SO2 NMP complex. So during the actual pilot scale processing, there was a number of modifications that were made, to the sparging vacuum level, agitation rate, and then obviously collecting FTIR data. It turns out the initial fit was okay, but not fantastic. Zero fitted parameters, a direct prediction of performance. What was proposed, though, was that additional reaction components, so for example, the substrate and intermediate from the previous reaction, as well as HCl, was impacting the degree of association between SO2 and NMP. So what we did is, by simply re-regressing some of those thermodynamic parameters, the enthalpy and entropy terms, we were able to improve regression quality substantially. So you see here, during the course of that run, again, where you're dynamically changing sparge rate, vacuum level, agitation rate, you see, commensurate changes in the fit that actually seem to regress very well against the lab scale data. So again, one of the challenges with a dissolved oxygen sensor is most types of dissolved oxygen sensor, whether that be a Clark type electrode or a photoluminescent type dissolved oxygen sensor, they typically display what is considered first order lag in their sensor response. So what we did is we took the evaporative solvent removal tool under gas sweep, which is the one that I showed for the SO2 system, and we added a sensor model into that. So this is essentially the first order lag expression that I was describing. It's pretty straightforward. Your actual liquid concentration, the difference between the liquid concentration and the electrode reading divided by some time constant, kind of follows a dCdx type, a dCdt type behavior. To implement that within DynoChem, it's actually relatively straightforward. That's two lines, right? So you have, in one case, you actually have that expression there, and then you have a conversion, essentially going from concentration to the readout of the meter, which is, in our case, was in parts per million of O2. Once we actually have that sensor model built in, we can use that exact same model that we had previously used to do a regression of the sensor model, of the sensor itself. So in this particular case, this is not a reaction per se, but what I'm doing instead is a simple instituting a step change in O2 level and seeing how the detector responds. Saying that a little bit differently, I started in aqueous that's saturated with air, and took out the probe and quickly moved it into a solution that was devoid of air. So you basically had been bubbling nitrogen through. So you go from a saturated solution to a completely free, O2-free solution, and you look to see how the sensor responds in time. Again, using that sensor model that I showed in the last slide, we were able to regress that time constant of that particular electrode. This particular electrode has a 14-second time constant. So at that point, I just want to kind of wrap up. So as I mentioned, kind of gas liquid systems you kind of run into them pretty routinely within the process of batch process development. Some of them some of them you care about, some you don't. Distillation, is obviously one that we spend a lot of time modeling. But here, what I hope to show is that by taking a moderately straightforward DynoChem model and making some, let's say, system appropriate tweaks to that model, that you can effectively use DynoChem as a tool to do simulations on vessel configuration, process parameter optimization, plant procedural improvements as well. And it allows you to, kind of move pretty seamlessly and efficiently between various systems in order to do that.